asymmetries. But before I do, I wanted to point out, it was brought to my attention the Fragos and McClintock paper of 2015. One way to deal with the lack of a gap in the black hole mass distribution between neutron stars and black holes is that there's actually accretion afterwards. And so even if you formed say in this case, I could have formed a 3 solar mass star, it could accrete a couple solar masses to make a 5 solar mass black hole. So these are the solid lines here are the black hole masses that you see. The dashed lines are what the black hole mass was at formation. So it could be there is a bias in that accretion is accreting the mass on top of these black hole systems. I said there wasn't that much accretion. For the simulations that I was using, there was not much accretion, but in these calculations, they could get over us. In some cases, you're comparing the same colors. So the light green to the light green dashed line, that's the difference between those two peaks is how much accretion the system got. And in some cases, the accretion is considerable and can dramatically change the mass of the system. So it could be that there are systems formed in the kind of 3 to 4 solar mass range that then accrete mass to get into the 5, 6 solar mass range. The other point I was going to make is that Fritz had shown a lot of stuff on turbulence and both Rayleigh-Taylor and Richtmeyer-Meshkov simulations. There are also experiments doing these exact things, and they do it at different length scales. So in this case, it's done at a 0.1 millimeter scale, but this is 400 microns big, but this is studying that Richtmeyer-Meshkov instability. This is a little bit bigger. This is about a centimeter in size, and there are experiments being done to understand how this turbulence behaves. It doesn't look as clean and nice mushroomy in the experiments. The assumption generally is that there's a lot of it's kind of messy when you do these experiments. It's hard to see nice, clean features. It's hard to make a 2-dimensional experiment. It almost always becomes 3-dimensional. And so it gets noisy when you try to make some kind of spectrograph of it. I don't suppose I could borrow your pointer again.
It should be on the table.
It should be on the table. Yeah, it's right next to my computer. Okay, so on the lecture. There's a lot of different ways you can imagine having an asymmetric explosion, so I want to go through what evidence we have for the asymmetries in supernova, why we think supernova are asymmetric in the core collapse supernova paradigm, and ways people have studied it and some of the observations that have convinced us that's true. So I'm going to divide asymmetries into 4 different classes. There's the spherically symmetric explosions. Those are what we get if we do a 1D calculation. You have whatever shell structure you had in the star persists through the explosion. If you do a spherically symmetric explosion in a multi-D calculation, you will get this Rayleigh-Taylor instability, and you will start developing some mixing, even just in a globally symmetric. It's symmetric calculation, but I'm modeling it in multi-D. If you add something like rotation to the system, you can get, or jets, you can get a bipolar explosion, so something that's axisymmetric, but now I have some asymmetries in the explosion. And at the very extreme, there's the globally asymmetric, where you can have a single mode flying out in one direction and having almost a unipolar explosion. So these are kind of the extremes that you could get. And I will go through, I'm going to first go through the evidence that pushed theorists to going in this direction. I will then go over some of the theoretical models that came out to explain these asymmetries, and then I'll come back to the observations and say, how do the new observations rule in or out some of these models for making asymmetric explosions. So we already discussed this. The first real hint that these supernova really had to be something that was asymmetric was that early emission from the gamma rays in 1987A. So these are those models that I showed you from Pinto and Woosley, where their initial predictions were that the gamma rays wouldn't really peak until 300 days after the explosion. However, the observations were much higher. The way that Pinto and Woosley explained this is they artificially, because they had a 1D code. So this is what the 1D calculation gives. If it was really truly symmetric explosion, it does not give the right answer. So we know we've ruled out that left top corner just with these observations. So they added some mixing, and now the question is, how do you make that mixing? You could either do it with, the idea was you need to have some break in spherical symmetry, but can you explain it with just I launch a shock and then I have mixing after the shock has been launched. If you combine, they also looked in 1987A and they looked at features in the iron 2 and nickel 2 lines, and they were very broad. So they had really broad features to them, so you had to have a lot of velocity. That velocity dispersion was way more than you could get with just a simple simulation of doing a global symmetric explosion. So if I take a symmetric explosion and blow it out, it isn't enough to make this kind of broad line feature. So at that point, the theorists realized they're going to have something that has some kind of global asymmetry. So it was a combination of doing the simulations in multi-D, trying to get that mixing out, and comparing to these broad line features. In addition to broad features, the features were redshifted. So you have a supernova going off, you're looking at the lines from the supernova, and they're redshifted. So if it was anything that was pointed at you, you'd expect it to be blue shifted. It's moving toward you. The lines from 1987A were redshifted from both the gamma ray lines and also some of these iron lines. So to explain that, you definitely need some kind of global asymmetry. In fact, you need the explosion to be stronger pointing away from you. So that's a global asymmetry. So another knock saying global asymmetry has to be there. Then there's a lot of stuff on remnants, and we're going to discuss this a lot more when I talk about nucleosynthesis, but just one feature of remnants is there was a structure here, and for the longest time, this was an argument for jets in supernova. There's a structure moving out in this direction where the iron and silicon have been shoved out further than some of the carbon and oxygen layers. So somehow you're really knocking material out in one direction. Turns out that this particular feature we actually believe is not an asymmetry in the explosion or in the something in the star, but actually in the circumstellar medium. But there are other features, and we'll talk about it in the next lecture, where the titanium distribution also shows evidence for global asymmetries. But I'll put that right down as a global asymmetry right now. And then the other thing that we had a lot of data on for a long time were the kicks in neutron stars. So if you look at the pulsar velocity distribution, most pulsars are moving at quite high speeds. These are assumed to have been produced in the explosion itself. So it's some asymmetry in the explosion itself. The simplest explanations all come from the momentum conservation. I'm going to eject material in one direction, the neutron star is going to go in the other direction. So that is what most of the mechanisms believe for neutron star kicks. So we have a lot of evidence piling up that there's definitely a break in spherical symmetry in the explosions, so you can't just do a 1D calculation. But we also have evidence growing saying that in addition, there has to be some kind of global asymmetry in the explosion mechanism. So there's a lot of mechanisms for these asymmetries. You can argue that I have the stellar structure. We talked about all this mixing and burning in the star before collapse. It is possible that mixing can have some asymmetries to it, such that when you collapse, those asymmetries grow and drive an asymmetry in the actual explosion, the ejecta, and allows you to mix out material. There can be asymmetries in the convective engine. So this is one that we've already discussed some, but we're going to just go through different possibilities in more detail today. And then there can also be asymmetries in the neutrino emission. I'll make a point here because we talked about some of how large are these Rayleigh-Taylor modes. It turns out if you look at mixing in stars, you can get as large as the convective region allows. So if I have a shell where here's the inner part of the shell and here's the outer part of the shell, the convection region the lowest mode is going to be as large as this region right here. So if you have a really huge shell, it's essentially the size of your entire convective region. So you can get to very low mode convection in a lot of these stellar mixing. And we also get kind of low mode convection, and I'll show you some images of this in the supernova engine itself. So the first one I was going to talk about is these asymmetries in the stellar mixing. Here's some models by Meakin and Arnett of the silicon burning layer, and you can see this is the convective region that they're studying, and these are those lobes. Again, they're as low mode as the size of this region, so that you get something that's roughly at the size of the silicon burning layer. The reason they modeled above that silicon burning layer is they noticed that there was gravity waves bouncing back and forth above that layer, and that affects the mixing, so that you can actually get some extended mixing if you include those gravity waves. So they were, not to be confused with gravitational waves, by the way. So these are gravity waves, the standard one. So why Kip Thorne and a few of us insist on calling gravitational waves, because there is a term for gravity waves, which is this bouncing back and forth that Meakin and Arnett are seeing right here. So you have some large-scale mixing in the silicon layer, then you let it collapse and you ask the question, what kind of motions can I get from the neutron star if I model this collapse? So here's a model at late times in that convective engine. So it looks very similar to the convective engine. Here's the star falling in. Here's the high entropy material. Here's the low entropy material flowing in. Here's that proto-neutron star. The initial starting point was at 0, 0. But as this asymmetric collapse progressed, the neutron star that formed started to move, and it's moving off in one direction. You can also see that then the entropy is much higher in this direction than in this direction, so it's causing an asymmetry in the actual motion of the neutron star. This produces kicks of, so Adam Rose has studied this and got kicks as high as 1,000 kilometers per second. We now believe that that was an artifact of his gravity routine in his code. I think with more realistic models, you only get about 100 or 200 kilometers per second by just putting in an asymmetric collapse, if the asymmetries are along the lines of what Casey Meakin and Dave Arnett produced. But this allows you to get some small level kicks, and it also seeds convection, producing some asymmetries in the explosion. Another mechanism is the caused by rotation. If you have fast rotation, when we were studying whether something is adiabatically unstable, we said, oh, if the entropy gradient is negative, you'll get large-scale convection. The simple way to picture this is if you have a blob of material and you raise it into a new region, and you raise it and you let it adiabatically expand, so you keep its same entropy, and you ask you ask the question, is it now buoyant or not? So if I raise it adiabatically and look at the density, if its density is now lower than its surrounding material, it's going to keep on rising and it's going to be unstable. So that's the simplest way to actually study, if you want to ask yourself, is something going to rise? Now, if I use the entropy, which is what Hans Bethe liked, if I use entropy as the criteria, I just look up and ask the question, is the entropy I've taken this thing, I put it into this new region, is its entropy lower than or higher than the region around it? If so, its density is going to be lower and it's just going to keep on rising. So entropy is the natural quantity. In a lot of stellar books, they use density, but what you have to do is raise it adiabatically and ask the question, is the density lower or higher? You can find the stability with that and do convection. Now if I add angular momentum adds another force. So if I go from a place of low specific angular momentum to a place of high specific angular momentum, then it's going to want to move back in because it has less centrifugal pressure pushing it up. So you can also look at the angular momentum gradient, and in a rotating star, if I have the angular momentum axis here, if I take a piece of material along the orbital of the angular momentum plane, if I move from here up to here and the angular momentum is increasing, it's now less unstable. It's going to want to move in. So I'm going to prevent convection along that angular momentum plane, but along the axis, there's no angular momentum, so there's nothing preventing that convection. And what ends up happening is your convection is stronger along the angular momentum axis. Now, this is only important if it's enough rotation to really affect the convection. But if you have any kind of rotation, if you have strong rotation, you will just in the convective engine naturally get an explosion that goes along the angular momentum axis. And it's just by stability analysis. And so this is what it looks like for a fast rotating calculation. This is colored by velocity speed. So up at these kind of dark red colors is 15,000 kilometers per second. In this region, it's going only a few thousand kilometers per second. And in this case, it's actually forming a disk around that neutron star of material falling back into the neutron star and driving a strong shock out here. This is going out to about 5,000 kilometers. So the shock now is already at 5,000 kilometers in the angular momentum axis. In the plane, it's only out to about 3,000 kilometers per second. 3,000 kilometers. So it's going much slower in this region. And so you're going to get a bimodal explosion. And so for fast rotating models, you can imagine getting strong asymmetries. This is a model done in 2 dimensions. If you do it in 3 dimensions, it's not as clear. This is a non-rotating model. The contours here are the upward rising bubbles. So here's the explosion moving outward, and these are the upward rising bubbles. They're kind of low mode, maybe 5 or 6 bubbles rising, but not one mode rising. As I start to increase the rotation from here to here to here, you start seeing more focused rising bubbles just along the angular momentum axis. So in all cases, this is the angular momentum axis. And you can see different features for what the bubbles are doing. If you look at this case, this is probably the first real evidence that you could get an explosion that's more unipolar, stronger along one direction than the other. So this rising bubble is much bigger than this rising bubble. And there's actually not much rising along that, the angular momentum plane. It's just along the axis. So these are the kinds of simulations you can get. With rotation, you can get a range of explosions that are more or less aligned with that angular momentum axis. If you don't have any rotation at all, but you can get, you evolve that convection for a long time, that convection can ultimately get into a single mode, and it'll slosh back and forth. So you can get really low mode convection. It turns out this used to be a sign of, well, maybe this is the standing accretion shock instability, so a specific instability in the star, but it was already predicted by Mark Courant in 1995 that everything is going to eventually go to low mode, even if it's Rayleigh-Taylor. And so this could still be driven by Rayleigh-Taylor, or it is the standing accretion shock instability. But Scheck et al. Did a simulation in 2D where they modeled this, and they ended up getting an explosion that really was only in one direction. So it was a one-directional explosion just from doing this turbulence correctly. This makes a strong low mode explosion that we can then compare to data. Unfortunately, this is done in 2D. A similar simulation done in 3D has less, it's not as one single mode structured, but it is still quite asymmetric. This is also done by the group in Garking, and they got a 575 kilometer per second kick. So this low mode convection can really get large kicks. if you can really develop into these low modes. Shekhinal got kicks up to over 1,000 kilometers per second. So, but you're starting to see in a lot of these models, really, once you get to low mode convection, you can get large kicks in the models. There are also models where you can invoke asymmetric neutrino emission. One of them was pushed by George Fuller and Alex Kosenko, where they looked at neutrino oscillations to sterile neutrinos in the protoneutron star core. So the idea they had was that in the protoneutron star core, if it's highly magnetized, the electrons will be aligned. There is evidence that there may be a sterile neutrino species. They then created a model where the electron neutrinos were emitted and then converted into sterile neutrinos, so they oscillate into sterile neutrinos. If they oscillate into sterile neutrinos, they didn't escape. But if you were in a strongly magnetized setting, there is a net direction for those neutrinos, and so you're throwing neutrinos out in one direction, and that carries away momentum. Momentum conservation says that that protoneutron star is going in the other direction. And so you can then study what happens to that neutron star. Here's with the emission rate predicted by Fuller and Kosenko. We modeled the kick that it imparted onto the neutron star, and the neutron star started moving in one direction, as you would expect. But then we studied the interaction with the outside material. It accreted, it changed the directions, it can produce a kick and a symmetry. The interesting feature is, in this case, the neutron star is going in the same direction as the strong explosion. So in the ejecta models for kicks, the ejecta goes one direction, the neutron star goes the other direction. In this particular model, the neutron star and the ejecta are going in the same direction, because it's neutrinos that are carrying away the momentum. There are also neutrino-driven mechanisms where it's if you look at the neutrinosphere and you have strong magnetic fields, those can alter the neutrino emission at the neutrinosphere. This is something that Aristotle Socrates studied with Omer Blaise, where they looked at the surface of the protoneutron star. They envisioned strong magnetic fields, and they calculated the neutrino emission rate, and they found instabilities that drove neutrinos off in one direction, producing a kick in another. So there are multiple ways of using neutrinos, asymmetric neutrino emission to drive kicks. The other ways are using the ejecta to drive kicks. So one of these two has to be true to make the large kicks that we're seeing. So we have these different mechanisms. I'm going to now go look at some of the observational data we have on these mechanisms and see if we can constrain what we know about the convective engine. So the first is these fast-moving pulsars. This is the Guitar Nebula. Here's where we think the supernova went off. This is the remnant, but the pulsar is off in this direction. We think that pulsar is moving more than 1,000 kilometers per second through the interstellar medium. And as it moves out, it produces the pulsar emission is producing a nebula, and you see a bow shock as it moves out. Here's another such system where you see the bow shock and the pulsar moving. So we see these strong kicks for the mechanisms that assume ejecta is driving the kick. You would expect the ejecta to be moving in the opposite direction as the pulsar. We don't have much evidence on these remnants which direction, where did the ejecta go with respect to the pulsar velocity, so it's hard to constrain that. For the models that are caused, the asymmetries are from rotation, you would expect the spin period of the pulsar to be aligned with the kick. So say I have, if it's a model like this, this one, where rotation was driving the explosion, I had a stronger explosion in this direction. I expect the kick to be in this direction. I expect the kick to be along the spin axis. So that's if rotation is causing the kick, then I expect the kick the spin axis to be along the same axis as the kick. In a lot of systems, this is true. But there are also systems where this is not true, and this is pulsar BO355 plus 54. This is that bow shock that you're seeing. So the pulsars we think is moving this way. And there's these kind of antennae-like structures going in this direction, which we believe is the pulsar, which implies that the pulsar is actually, the spin axis is here. So I have a spin axis that's lined here, but the kick is in this direction, so it's almost orthogonal to the spin axis. So in this case, I think it's very hard to explain this with any kind of angular momentum, jet-like, or bimodal explosion. This particular neutron star seems to be kicked in that opposite direction. Some of the convective engine models predict this kind of ejecta mechanism, so this would be fine for a lot of the normal convective models, but it means that rotation was not playing a big role in the asymmetry of this explosion. So the kicks are big, and that's going to be one of the hard things for us to try to explain is how do we get these very high kick velocities. This is the birth velocity of the neutron stars. This is the distribution. There were several models that fit. There are models that are bimodal where you have a low velocity feature and then a high velocity feature. So this is one of the kick velocity distributions that people expect. This is from Arzumanian et al. 2002. They could also fit the velocity distribution with a kick distribution that's more just a single Maxwellian with a peak around 450 kilometers per second. So either of these two kick mechanisms fit the data. A comment on this is one of the hard things about getting the pulsar velocity distribution is the understanding the distances of these pulsars, and previous velocity distributions were much lower. The velocities increased when they realized that the dispersion measure used to get the distances to these pulsars was off, and by fixing it, they ended up getting a much faster velocity distribution. So whatever kick mechanism we need to be able to explain these really high velocities, and it's not a straightforward thing to be able to explain. The ejecta mechanisms can do it if the asymmetry is large, but it's difficult for those mechanisms to get the highest velocities. The kind of bimodal explosions where you have lots of rotation are more likely can explain really large kicks. The problem with those mechanisms is that it looks like the kick distribution is not always aligned with the rotation axis. So there has to be some way of getting around that. That is not in the current data. So kicks have played a reasonable role in trying to constrain what we know about our explosion mechanism. Right now, I think the consensus is that the neutrino mechanisms are not needed. They usually require some kind of fantastical belief. You have to, invoke a little bit more new physics, things like neutrino oscillations, sterile neutrinos, large magnetic fields. You don't need that with the ejecta mechanisms. So although I've worked on a lot of neutrino mechanisms, I'm probably also leaning toward ejecta mechanisms making the kicks. The other asymmetry I want to talk about is the explosive asymmetries and the gamma ray emission. So if you take different explosions where I say, I have a bimodal explosion or a single lobe explosion that's stronger in one direction, you can calculate where's the nickel distribution at late times. So here's a set of 4 calculations where this is just a spherically symmetric explosion run out in 3D. So you get some mixing because of that 3D explosion, but the nickel's more focused in the center. Here's an explosion where it's a bimodal explosion like what we got in those fast rotating systems. Here are 2 explosions where instead we assume that there was a strong explosion in one direction. So a unipolar explosion with a different opening angle. This one has a 20-degree opening angle. This one has a 40-degree opening angle. So it's 2 different models. this is the contours here are the nickel distribution. So in the symmetric, it's very centered, still in the center. It has mixed out some. In a kind of bimodal explosion, you can get mixing out along that pole. In a very focused unipolar explosion, you can get nickel mixed out to the outside of the star and get nickel moving out through the star. You can then compare these results to the gamma ray emission, that early rise time of the gamma rays. So here's the gamma rays coming out, and hard X-rays and gamma rays coming out with time. And you see here's that symmetric explosion where we argued that a simple symmetric explosion doesn't mix enough to get the light out. So this is the log flux, and this is in energy. So this is at 150 days, 200 days, 250 days, 300, and 365 days. At around 300 days, the asymmetric and the symmetric explosion get roughly the same gamma ray signal. But at early times, at 150 days, where in 87A we saw really early emission, only the kind of asymmetric explosions can explain it. And the blue and the red here are that jet model that we had. So I'm just comparing this model here. That model, if I look along the pole or the equator. So it doesn't matter which, the nickel gets mixed out, I'll see it whether it's pointed at me or not. So I still get those gamma rays coming out, even if it's not pointed at me, and I get it out early at the 150-day level if I have any kind of asymmetry. So the asymmetries easily explain that mixing model, whereas a symmetric explosion in 3D does not. And that we've known for a while. The other feature that you can start explaining is if you have a single lobe explosion, you can start explaining this kind of redshift line. So here's a symmetric model. Well, this is still the jet model. So this is the symmetric model. This is that line width. If I do the bipolar model, I start to get a thicker line. If it's pointed at me, I get a blue shifted line because the region that's coming at me first, I see more emission from. So again, this is 200 days, 250, 300, 365 days. So there is a blue shift in the lines if you use a jet model. So I can explain a shift in the lines, but it's blue shifted with the jet model. So that is not the observation. The observation is that it's red shifted. So the question is, can I explain the red shifted line? And that requires some model that has a strong explosion in one direction. So here is a strong unilobe model moving out in one direction. These plots are looking at different angles. If I look along this line of sight, this is the velocity motion of the material I'm seeing. So if I see it along this line of sight, I'm seeing velocity that's blue shifted. So I see stuff that's coming at me. If I'm looking along this line of sight, I'm seeing this material as it comes out, but now it's redshifted, it's moving away from me, and I can start to reproduce that redshifted line. If I look in this region, I see a broadened line, but it's not redshifted, it's broad across the 0 point. If I'm looking along this direction, I again get a blue shifted line. So depending on the viewing angle, I can get a blue shifted line, a red shifted line. If you're right along this case, at this time in the calculation, there's not much emission at all. But this is the kind of range of emissions I can get just from looking at these lines. So the issue is I need to explain some kind of redshift in the line. I need to have some way of producing a single lobe explosion. So it really starts to argue for either a explosion that is more like this, a rotating model, but it's much stronger in one direction than the other. So it has to have that low-mode convection. Or it's arguing for some model like this that Sheck et al. Did, where it started sloshing back and forth, and then when it drove out an explosion, it drove it in one direction. And I guess this is the more realistic one you should look at. This is a 3D model where it doesn't look as clean. It's not like there's one single lobe going out, but there is a stronger explosion in one direction than the other. So it really does require something that, in the end, produces a stronger explosion than in one direction than the other. Supernova 87A is very indicative of this. If you look at the titanium line distribution, it has that same redshift in it. So it looks, the evidence is getting larger and larger that this kind of low-mode convection really is true in a lot of these supernova models. So the observations are really pushing us in that direction. It seems to explain a lot of the data, but now we're in a position where we can start ruling in and out our models. So if you have a magnetic field model, it's really hard to make that magnetic field model. They're very symmetric. So you look at an AGN, the jets are fairly symmetric. It's hard to make a model that is magnetic field dominated not be bipolar. But the supernova that we're seeing are. And so this is further evidence pushing toward this kind of convective engine that goes down to low mode convection is really driving the explosion. So that's, the evidence continues to grow on that. So we've talked about these two asymmetries. It turns out that there are other ways of looking for asymmetries in supernova. One of the ones that would be really nice would be gravitational waves, and we're going to talk about that probably Friday, where we go into more detail on what kind of signal, what can we use gravitational waves to actually constrain the engine, how can we use the gravitational waves to constrain the engine. They probe down near the core, so you can actually study the asymmetries with gravitational waves. Unfortunately, we have not detected supernova for gravitational waves, and as we'll discuss on Friday, it will require a galactic supernova to really, unless stars are rotating much faster than we think, it'll require a galactic supernova to observe gravitational waves. The nucleus synthetic yields are also a good indicator of some of the asymmetries, and we'll discuss that in detail in the next lecture. In particular, the Cassiopeia A titanium results by strong constraints on the asymmetries of the explosion. And it's possible that you could use the light curves to observe these asymmetries, but there's a lot of work that has to be done to use light curves to constrain the theory of the engine. So let me just, this way we actually can finish roughly at the time that we were planning. So Fritz and I planned this well to get you guys in a rough, good finishing time. To match the mixing in supernova, we need some kind of asymmetry in the explosion. You cannot just produce it by driving a spherically symmetric explosion through the star. So that asymmetry can come from either asymmetries in the collapse, it can be asymmetries in the explosion, but one of those two things are needed to try and produce the mixing that we see in the stars. The different engines fit into two places. If it's a rotationally induced mechanism, something like either this rotationally confined convection or magnetic fields, magnetars, jets, they produce bimodal explosions. The kind of just convective engine is more likely to produce low mode explosions where it's more focused in one direction than the other. It is pretty clear from the evidence from both pulsar kicks and from the gamma ray lines, the redshifted lines that we see in 1987A, that this low mode kind of single lobe explosion is more common. So we see this in now several explosions. That is telling us that the mechanism in the end can't be something that is dominated by the rotation and driven in a jet-like structure. It has to be something that's more low mode. So the evidence is pretty strong there. I have not seen anybody work out a way to explain that if they're using a magnetar or jet explanation. And so until that happens, it really makes it a less viable mechanism for most supernova, at least the supernova that we have detailed data on. I think that where we're going to see really strong evidence for these kind of asymmetries is when we start looking at the nucleus synthetic yields. And there's a lot of, with that data, it pretty much seals up the fate for any kind of bimodal explosion. It really has to be this low-mode convection. Now you can come up with a way to do this, but that's the observation you have to match the observations. So the asymmetries are definitely providing strong clues to the explosion. Many of the proposed engines produce these bipolar explosions, but really you need to look for something that's going to produce asymmetries that are less than bipolar, so lower mode. And the next lecture we'll discuss the nucleosynthetic yields, and that will go into great detail on what are we actually looking at for trying to probe these asymmetries. When you're looking at nucleosynthetic yields, the caveat that I would place for you is the mistake we made with CAS-A initially was we believed this jet-like structure here. So they had a jet and a counterjet in CAS-A, but that is material that is, a lot of it is like the silicon, the iron, but it's not clear where that iron was produced. The silicon layer, it's also not clear where it was produced. And when you just look at something that's lit up by being shock heated, you can be mistaken on what the true asymmetries of that material are. In fact, there's asymmetries in the iron, but there's no iron seen in the center of CAS-A. The reason there's no iron seen there is it just hasn't been shock heated yet. So we really don't know the asymmetries when we're just looking at something that's shock heated. When we want to use nucleosynthesis as a constraint, we have to use something that's more solid. And in that case, it has to be something that you see whether it's shock heated or not. And that is what NuStar's goal was. NuStar's goal was to look at the titanium distribution. We see the titanium through its decay lines. So we see it whether it's been shock heated or not. And then the confusion from some of these remnant observations goes away. And it actually paints a very different picture for this explosion than this kind of jet-like feature implies. So in fact, in the end, I think this jet-like feature was an observation that led us astray, and in the end, the titanium is more important. So when we talk about nucleosynthesis, we'll go how nucleosynthesis can constrain the results, but be careful whenever you're looking at data. Some of it can lead you in the wrong direction. In the case of CAS-A, it was this strong jet-like feature, which there were scientists that had explained it with circumstellar interactions, but until we actually saw the titanium, we couldn't prove that. And with this, I'll end on asymmetries. We're back on time, 10:30, so you can go do your skiing. And I'll end there.
Before coffee and skiing, maybe you have some questions?
Yes, yeah, I have one considering the high kicks on your calculations. So you suppose that kick is high, basing on your pulsar velocities, high pulsar velocities.
Yeah.
But it seems to me that what is more important is to explain the observational fraction of double neutron stars among the total number of pulsars. And if you take, for example, like Taylor type pulsars, it means that where you have two neutron stars, so it means that system survive in two supernova explosions. And if you take 500 kilometers per second, 1,000 kilometers per second, you destroy almost all the systems like this, and you will not be able to explain what we observe, the number of the double neutron star binaries among the total number of pulsars.
So it's true if I take 1,000 kilometers per second, it's hard to make them remain bound. Even 500, unless it's a really close system, it's hard to make them remain bound. But if you have a distribution like this only really cuts off about half of your total. Yeah, it is two-peak distribution, which fits the pulsar data. It also can make a rate that is comparable to what we need in neutron star mergers. So it's at this point, most population synthesis models use either this kind of bimodal peak or this one, and they are making enough neutron star. They don't explain if the rate were really high, they would not explain the neutron star merger rate. But the rate that they're predicting, the rate is not extremely high, otherwise we'd be seeing them in the LIGO band. So the rate that we're predicting actually from these kick models seems to be the correct rate. So right now, putting in this kind of kick distribution seems to produce a double neutron star merger rate that is reasonable. Now, the issue with these, whether something remains bound or not depends both on the direction of the kick and actually how close the system is before collapse. And there's evidence that there's more and more systems go through not just a hydrogen common envelope, but a helium common envelope. And in those cases, it's really easy to make them remain bound.
But are there any possibilities to explain this high kick without, not high kick, high velocities of pulsars without these very big NATO peaks? Because you have like binary system, you have a specific angular momentum from the orbit, so you can use this to make big velocities.
So there are kick mechanisms where there's interactions in dense clusters where you can kick out your neutron stars and you can get kicks from there. And you can imagine a dense open cluster maybe making kicks for things in the protoneutron star. There are engines where after the neutron star has formed, you can get a magnetic propeller effect and drive the system post formation of the neutron star and try and get a kick there. That is neither of those are the consensus view for how the strong pulsar kicks are getting produced at this point. Is there any other mechanism that I'm missing? The consensus view is it does happen in the supernova, and it's just these fraction aren't going to make your double neutron stars. It's going to be the slower velocity ones that make the double neutron star systems. You actually need a kick. So depending on how you're going to make your double neutron star system, some of these need kicks just to get the right orbital parameters in the neutron star system after the binary evolution.
The question is how big it should be.
Yeah.
Necessarily that it's 500.
So you can imagine. Yeah, so you could say for these, but again, like I said, this is only changing the rate by a factor of 2 by saying the fast ones don't remain bound. We are not that close to predicting the rate of neutron star binaries to within a factor of 2. I think the various estimates of the rate of binary neutron stars based on the observed systems that we have. So you can do a rate of what's the formation rate of binary neutron star systems by asking, I look at the systems that I observe, the closest one has a merger time of some number of years. So I can say, to make that closest one, it has a volume associated with it. It also has a merger time associated with it. What would be its rate? And if you do the simplest possible thing, the rate of binary neutron star systems is huge. And in fact, LIGO ruled that rate out. So not even advanced LIGO ruled that rate out. So we know that simple approximation of what is the rate is not correct because it predicted that LIGO, not advanced LIGO, would detect neutron star mergers. I mean, it predicted, I think, nearly 100 neutron star mergers observed with advanced LIGO very quickly. So that rate is really high, and you could not explain that high rate with this kind of kick distribution. But the rate of neutron star mergers that we're predicting with these kinds of kick distributions right now is one of the few rates that's consistent with the binary neutron star system. So right now, this high kick distribution is almost needed to explain the low rate of neutron star mergers, not the other way around.
Another question?
So you spoke about these low modes in the engines. elaborate on these?
So there's no there's no magic. I mean, so in fact, any instability, it turns out if you turn on any kind of convective instability, and I have a region where it's convecting from some inner radius to some outer radius, the size scale of the convective instability can grow to nearly the R outer minus R inner. Typically in models, that's where it grows toward. And it depends on how much time you convect, whether you go to those low modes or not. So if you have a 20 kilometer neutron star and a 400 kilometer outer radius where the star is falling in, you can get modes that are as big as 380 kilometers. And if you go a little bit further, those modes start to it gets so big that it's the entire size of the convective region. And we see this in, I wish I had the movie of Paul Woodward. He sees this in the convective region of, in the helium burning shell of massive stars, where he sees this sloshing back and forth. This convection is just going all in one big mode of convection. So it's just where convection will evolve to if you're given enough time. And so there's lots of little structures on top, but the largest mode will be as big as your convective region if you give it enough time. So the energy, I guess the way to say it is, you look at that Kolmogorov scale where you look at where the energy is included, and it'll go from the largest scale you have possible down through the Kolmogorov scale till viscosity determines your lowest mode. So you have this Kolmogorov scale, it'll go through the full region, but what you'll see in the end, and for supernova in these asymmetries, it's that largest mode that makes a difference. For a while, we were arguing this was an indication of the standing accretion shock instability only. But there was a paper in it's funny, we thought that, but in 1995, Marc Harant had written a paper saying Rayleigh-Taylor will do this as well. So there's, I mean, it's in the literature for supernova from 1995 that you will go down to these low modes. And that's where the convection will go toward. Now, the standing accretion shock instability has an interesting feature in that it's more like how a whistle works. So it's actually pressure waves. You're actually converting, your accretion energy is driving pressure waves that are driving the instability, and it should look different. It turns out that we as theorists are bad at looking at our calculations and determining whether Rayleigh-Taylor is dominating or this standing accretion shock instability is dominating. It's kind of hard to extract that physics from the calculation. You would think it would be easier, but we can't do it. In my calculations, it's almost always, I can see that it's entropy driving the convection, but I think in Thomas Janka's and Tony Metzacappa's, they actually, in the case of Tony Metzacappa and John Blondin, they intentionally removed the Rayleigh-Taylor instability to see what other instabilities they could develop, and that's where the Saas-Fee clearly was dominating in theirs. But in either case, you can get low mode convection. So it's the convected instabilities will go up until they get the largest scale will go up to the size of your convective region. And so that's how you get the low mode. If it's really low mode, it means you really took a long time convecting. If you only have a short amount of time, you'll see a lot of the higher mode instabilities dominating. It takes some time for the energy from the high modes to go to the low modes. And so you have to convect. It means you have to have more cycles of convection before you get there. But if you have those cycles, you'll get to low mode.
You showed a plot of the view angles in the bottom plots from the simulation.
This one?
Yes, so if you consider like the example of observed supernovas, could some of the weak supernovas just be a matter of the viewing angle that you observe the supernova in?
This is only in gamma rays. So in the optical, you actually see a brighter light. This is just looking at the gamma ray flux. So you're saying a weak supernova, can I be seeing just a weak explosion in my direction? So this is not, I did not do, I am not making a plot of, this is just in the gamma rays. So the gamma rays are a function of where's the nickel closest to me, whereas the light curve from the supernova itself, I would guess that this explosion is still fairly bright in this direction. But there is a dependence on the direction for these asymmetric explosions, the light curve, but it's much less extreme than these cases. In this case, it goes from a strong signal to almost nothing. In the optical, and the reason is the optical is redistributed light, it's shock heating, it isn't actually powered by the nickel. You will still get a fairly bright signal in that other direction. And in fact, 87A is a classic case of this, because 87A, we think we were at this viewing angle of it, and it was still a fairly bright supernova. It was a little bit weaker, but it was still a fairly bright supernova. And part of the reason here is that 87A was not, the nickel in 87A was not what powered the light curve until late times. So the peak brightness of 87A was done by shock heating instead. I think this kind of asymmetry will be harder to see in the optical and harder to detect in the optical. And so the weak supernova that we're seeing, I don't think you can explain them just as I have a single lobe that's going really strong in this direction and not strong in the inverse direction.
So let's try this again.